right, we're going to continue onward today. Hopefully, Trevor can.
I'll tell him. I feel like you remember that.
Well, with the screencastify that we have, I don't know. Has anybody talked to him?
Yeah, it said he's got a cold.
Huh?
It said he got a cold.
Okay, what we're going to talk about today is continuity. We talked about discontinuities already. But we're going to talk about continuity and proving things continuous. When you're talking about a function that is continuous, there's a function if the graph has no interruptions. The function is continuous if the graph has no interruptions. So if we talk about the idea of interruptions, if you have no interruptions, the function is continuous. Well, what do we mean by interruptions? Well, what we mean by interruptions is you have no open dots, you have no discontinuities, no vertical asymptotes there. A graph can be drawn. Another way of stating this, a graph can be drawn without lifting your pencil from the paper. So you're looking at a graph, and you're going to be able to draw this graph without lifting that pencil. It is a smooth graph. So if I'm looking at x and f of x, it is a smooth graph that continues onwards. When you have a discontinuity, which we'll get into with respect to our graphs here in a little bit, you get vertical asymptotes, you get open dots. Those are not continuous graphs. Well, this section, what we're going to do is we're going to look to prove that a function is continuous. We're proving that a function is continuous. And you have to write out and show 3 steps. There's a 3-step process to this. The first step is you must show f at a exists. You plug in a for x and you find a value. You come up with a value for f at a. That's your first step. Your second step is you need to show that the limit as x approaches a exists. So the limit must exist for the function at a value of a. Well, for this to occur, we have to show 2 things. Or we have to show 1 thing, 2 different limits. We must show the function, the limit as x approaches a from the left of our function equals the limit as x approaches a from the right of our function equals the value of L. We must show our limits as we approach from either direction equals each other, equals some value. If the limit as x approaches a from the right equals the limit as x approaches a from the left, then the limit exists of the function. So how you prove that the limit exists at a value of a of a function is show the limit as x approaches a from the left and right equal each other. If they equal each other, then we have a limit there. And the third step to this is we have to show f at a is equal to the limit as x approaches a. Basically, step 1 equals step 2. So we take a look at some problems. We want to prove that this function f of x equals x over x plus 3 is continuous at x equals -3. So we have a 3-step process that we have to go through. Step 1, we have to show our function f of x exists at x equals -3. So we have to show this. So we plug it in. F at -3 is equal to -3 over -3 plus 3, which is -3 over 0. Is this defined? No, not defined. This does not exist. Hence, function is not continuous at x equals -3. QED, we is done. Another example. We have a piecewise graph. F of x equals 2x for x greater than or equal to, or greater than 2. But for x less than or equal to value 2, our function is equal to x minus 1. First thing we need to show is that f at 2 exists. So we need to find what is our function value at a value of 2. Well, which one of our lines are we going to utilize to find our function value 2? Will we use the top one or the bottom one? Noah? Top one, why?
You plug it in 4 is greater than 2.
But I'm showing that I just want to find my function value 2. So my x value is a value of 2. We use the top function for values of x that are greater than 2. Is 2 greater than 2? That's not. So I'm not going to use the top function because I'm not greater than the value of 2. But if I look at the second line, I have x is less than or equal to 2. That would work. So we have 2 minus 1, which is a value of 1. So our function value exists at a value of 2. The next step is to show the limit exists at the value of 2. So we have 2 different limits that we have to solve here. We have to take our limit as x approaches 2 from the right, and the limit as x approaches 2 from the left. So if I'm looking at the limit as x approaches 2 from the right, am I going to use my top line or my bottom line here? Which ones are values that would signify values that approach from the right-hand side of 2 or bigger than 2? Preston? Which one of our functions show that? The top one, because those are values of x that are greater than the value of 2. So when I'm approaching 2 from the right-hand side, I'm approaching from this value from this direction here, which are values that are greater than 2, and my piecewise graph tells me that I'm going to use my top line. So we have 2 times 2, which is a value of 4. As I approach 2 from the left-hand side, which one would we use now, Noah? The bottom one, because these are values of x that are smaller than the value 2. So we have 2 minus 1, which is a value of 1. Well, for a limit to exist at the value 2, limit as x approaches a from the left has to equal limit as x approaches a from the right. Do we have that? No. Limit does not exist, because the limit as x approaches 2 from the right of our function does not equal the limit as x approaches 2 from the left of our function. So that limit does not exist. But if we take a look, the limit as x approaches 2 that should be from the left here. The function value at 2 equals the limit as x approaches 2 from the left. These values are equal. Limit as x approaches 2 from the left equals 1. Limit as x, or function value 2 is the value of 1. So when this happens and this occurs, we can still make a statement and say, since these two are equal, we are going to be continuous from the left. Because as I approach x from the left, or 2 from the left, I equal my function value. So that gives us a second set of scenarios that could occur. If f of a is equal to the function of x as we approach a from the right, we can say we're continuous from the right. Or we could do the exact same thing and say we're continuous from the left. So if our function value only equals the limit as x approaches a from the right or left, we can be continuous from that direction. Let's take a look at another scenario. First, we need to show our function value. We have f of x is equal to x squared. For x not equal to 0, it's equal to 5 for x equal to 0. What's our function value at 0? What's our function value at 0, Preston?
5.
5. Because our function value is equal to 5 for x equals 0. So we need to show the limit exists. So we take a look at our function value, our limit as we approach 0 from the right and the limit as we approach 0 from the left. As we approach 0 from the right, what is our limit? Well, what we are saying here, once again, is we are getting that delta away from 0. We're getting that small value away from 0. We're never equaling 0, but we have 0 plus this delta value. That very small number. So we're using 0.1, 0.01, 0.001, 0.000001. What is our function value approaching as we are getting closer and closer and closer to the value 0? 0. That's correct. Because if we are not equaling 0, we have to use this function up here. And what we're saying is we're 0 plus this delta value. So we're not equaling the value 0. We're this delta away from it. We're 0.1 away from it, or 0.01, or 0.000001 away from it. But we're not equaling a value 0. But our value is getting closer to value 0 as we approach 0 from the left. So this is a 0 minus delta. So we have negative 0.1, negative 0.01, negative 0.00000001. What's our y value getting closer to? Also 0. It is also 0 because we are not equaling a value 0. We're getting closer and closer to the value 0, but we're never equaling that value 0. We're that delta away from it, that plus or minus delta away from it. So if we're plus or minus delta away from it, we're not equaling 0. So we have to go to the top function because our top function are for values that are not equal to the value 0. So if I take the limit as x approaches 0 from the right, this equals the limit as x approaches 0 from the left, which is a value of 0. So the limit does exist. The limit exists at a value 0. So the third question is, okay, I made it through the first 2 steps and I'm still good. Does my function value of 0 equal the limit as x approaches 0? Does step 1 equal step 2? Does our step 1 equal step 2? Our function value at 0 is 5. Our limit as we approach 0 is a value 0. Are those equal, Preston? No. Okay, so does these equal? No. They do not equal. Hence, we are going to be discontinuous or not continuous. So we have one more scenario to go through. We want to prove this function is continuous at a value of 2. Okay, show f of 2 exists or is equal. Well, which line do I use if I'm finding my function value of 2 now? The bottom one. So we have 2 plus 2, which is the value of 4. Should be a 2 there. So we're going to approach 2 from the right and left now. Once again, we're getting that delta away from 2. So we're going to approach from the right and to the left. Well, as I approach from the right, I'm talking about values of x that are greater than the value of 2. Which function should I use here, Preston? Which function tells me values that are greater than the value of 2?
2x.
2x. So I have 2 times 2, which is a value of 4. As I approach 2 from the left-hand side, now I'm using values that are smaller than the value of 2. So now which one are we going to use? The bottom one, which is 2 plus 2, which is a value of 4. Does the limit exist? Do these two values equal? Yeah. So the limit exists. At a value of 4. So the question is, does step 1 equal step 2 then? Yes, they do. Hence, we are continuous at that value of 2. What we basically have here we have this for the first graph, and our second graph, we fill in this dot, and we have this. So basically, our closed dot we have with the first graph is filled with this open dot, or the open dot we had to start out with was filled with a closed dot. So our graph would look like a continuous graph. We have no hiccup there. If I would take a look at my graph, this one here, what this graph would look like this would be what this graph would look like. We'd have a parabola down to the origin, then we'd have an open dot there, and we'd have to finish the parabola out there. But this dot would not get filled in. I would have a dot up there at a value of 5. So I have not a smooth graph to get all my points in there. I'd have to come down here, I hit this, then I had to pick up my pencil, and I had to go back down here and finish my graph here. So you're picking up your pencil to be able to finish your graph. I have a second sheet for notes. Must have pulled the wrong notes out here.
Intermediate value.
Yeah. All right, just hold on a second. Intermediate value theorem. For a continuous function on a closed interval from a to b, if a subscript 0, which is called a or y naught, y subscript 0, y naught, is any value between f of a and f of b, then y naught is equal to some function or function value at c for some value c on the interval from a to b. If I have some interval okay, if I have two values, f at b and f at a, okay, f at b and f at a, and y naught is between here. So we're saying this y value is somewhere in between there. I have f at b and I have f at a. If my y value is somewhere in between these values, then there exists a value of c on the interval from a to b. If a and b, if y is between f of a and f of b, then there's a value of c in between a and b somewhere along the line. We want to solve the equation using the intermediate value theorem. We have x cubed plus 2x plus 1 is equal to 0. This is our function, f of x, is equal to this value of 0. Okay, I'm trying to find this y value or the c value as our function value is the value of 0. So this is your y naught. This is your y naught. And I want to solve this equation somehow for that reason, or between that. Well, what we need to come up with is we need to come up with an interval. We need to come up with an interval. You know what? I'm going to pause there. I'm just going to keep where we're at. We'll start up tomorrow with respect to the intermediate value theorem because it's going to take us a little bit longer. On page 180 or 124, you have 17 to 24, Monday's assignment. Basically, what you're dealing with is you're looking at proving continuity, proving your continuity. Tomorrow we'll start off with the intermediate value theorem. We're going to prove the continuity there. 17 to 24. All right, questions? The rest time is yours.